Hello everyone and welcome back to this next lecture. So this is where we had left off in the previous lecture where we had run the simulation and we had seen these results. So in this lecture I'm going to analyze these results. So let me just expand on this and let's start. I'll just put grids everywhere just so that I know what I'm looking at. And now let's start with the very first one. So we've already seen the gate voltage. Now let's go and look at the output voltage. So for example here we have plotted the output voltage with respect to the input voltage. The input voltage we know is 24 volts and we see that the output voltage is, let me zoom in a little, and you see it's just below 12 volts. Right? Now in case you're wondering why it's slightly less below 12 volts, that is simply because there are resistances in the circuit. The inductor has a resistance and the switch also has a resistance, which I'll talk about very soon. Right? So this means that we have actually stepped down our output voltage by half. And if you notice, if you come over here and have a look, you will notice that we've chosen a 50% duty ratio, or our D is 0.5. So with a D of 0.5 or a duty ratio of 0.5, we have already seen in the previous lecture that the output voltage is simply the duty ratio multiplied by the input voltage. And therefore, with the input of 24 volts, we are expecting an output of 12 volts. And if we come over and have a look, we'll see that is indeed the case. I would say go ahead, play around with this value, try to change it, try like 30 microseconds, 70 microseconds, play with this and see what you get, right? So this is something I will leave to you as an exercise. Now let's come over here and have a look at the inductor current. So let me zoom in. And if you take a look, now here for instance, okay, let me just pull this up and let me bring this down. So I'll just drag this down. This is a very convenient feature in QSPICE. And here you can see I'm just comparing it with this gate pulse. So for instance, when this gate pulse is high, the switch is conducting. And when the switch is conducting, you'll see that the inductor current is rising. And when the gate stops conducting, that is when you'll see that the inductor falls. Now at this point of time, we can actually go and add the other one as well. So let's say for example, I have ID1. Let me go and add ID1 as well to this. So for instance, if I say add plot and I click on ID1, now the diode current is also added to it. So you see here that when the inductor current is increasing, the diode current is at 0. I'll just zoom into one particular cycle. So when this inductor current is rising, when the switch is turned on, at that time the diode current is 0. And when the switch is turned off, it stops conducting, that's when the diode current takes over. So this is when I say that the inductor current finds a path to freewheel. So for example, when the inductor current starts to drop, that is when the induced EMF of the inductor is such that it forces the diode to be forward biased, and therefore the diode picks up the inductor current and the inductor current continues to flow. So this clearly shows the changeover between the inductor current from the switch to the diode and then back to the switch again. So when the switch is turned on again, the diode is reverse biased by the input voltage and the inductor current starts flowing through the switch again. So this clearly shows that this is the buck converter. So now let's go and have a look at the output voltage. So let's say for example, if we take a look at the output voltage as well. So here the output voltage, I have also zoomed in the same period. You'll see that when the switch is turned on, the output voltage also rises. And we've already seen that. We've seen that when the switch is turned on, then the input supplies energy to the output and also the inductor. And that's the reason why the inductor current rises, and also the voltage across the output capacitor also rises, right? And of course, when the switch is turned off, then in that case, the output voltage starts to drop because the output has to supply the resistor, the load resistor, and the current in the inductor, or rather the energy in the inductor, is not sufficient to maintain the charge of the output voltage, right? Or rather the output capacitor. So this clearly shows that we have now a working DC to DC buck converter, right? Now there are a few issues and you might be wondering, for example, why is our output less than 11.2 volts? And here, of course, you should go and have a look at some of the other parameters here. So for example, if you take a look at this, we've seen already that there is a series resistance. So for example, I've added a 0.1 ohm resistance to the inductor, right? Now, of course, if you do know a more practical value of an inductor resistance or the equivalent series resistance of an inductor, then by all means add it. But remember that this resistance is not just the winding resistance of the inductor, but it's also a representation of the losses in the inductor, the core loss, the hysteresis loss, and other magnetic losses that may be there. Similarly, this capacitor Cout also has its own series resistance. But there is one series resistance that we must take into account, and that is of this switch. So let me go and have a look. Now you'll see here that there is an off resistance and there is an on resistance. Now if there is an off resistance and on resistance, you'll see that there is a model value, which means that this is some model which is used by default. And if you take a look at this, this is the model parameters. And you come over here and have a look, you'll see these are the values it is using. So the off resistance is 1 mega ohm, and that's pretty big. But look at the on resistance. The on resistance is 1 ohm. That's pretty huge. That's a huge on resistance. So therefore, for that reason, let's go over here and have a change and change that. So let's go and change this to, let me see what the value is again. It is R capital on, so I should write R. Make sure you write them in exactly the same case. I don't know if it is case sensitive or not, but it's always a good idea. So I'm going to make this 10 milliohm or 0.01 ohm, right? Because that's typically how these are the kind of resistances that MOSFETs and IGBTs will have when they are conducting. So let me go and run the simulation again. And we should have got some result. Let's come over here. And now let's take a look. So let me zoom into the output voltage. And you can automatically see the result. You see now it is 11.5 volts, right? It is almost 11.5 to 11.6 volts. So you see now there is only a 0.4 volt drop from the required output voltage. And this is only expected. Now this would be corrected once you have a closed loop control, because in that case you're going to regulate this duty ratio in order to achieve the exact output voltage you want. Again, we won't talk about control because control is specific to each and every DC to DC converter, and that is simply not possible in this course. So with this, we have achieved a basic buck converter operation. By no means is the simulation over. First and foremost, we must include a proper pulse width modulation. We have just generated a pulse voltage, right? But we should generate a proper pulse width modulation, and later we should replace this switch by a MOSFET. So that is coming up in the next couple of lectures. But before that, if I would say go ahead and play around with this circuit, change the duty ratio, change maybe even the switch parameters, play around with the capacitor, the load, everything else, and see what you get, right? This is something I would leave to you as an exercise before you continue. Now, if there are any other doubts, such as any other issues, something didn't work, or you have some other error, you are trying something else, post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much for listening, and goodbye for now.